All right, class, in this lesson we're going to take a look at number theory. And in number theory, we're going to be dealing with natural numbers and specifically how we can figure out whether something is prime and whether or not it has factors. So we're going to be dealing with prime numbers and factors here. And so this long definition says that if a number goes in and doesn't have a remainder, basically, it is a factor. So zero remainder is the key as to whether or not something has a factor using long division. Okay, so prime means that you've got a natural number greater than 1, and the key here is greater than 1. In other words, 1 is not prime. That has only itself and 1 as a factor is called prime. In other words, no number goes in evenly. So if a number is not prime, it is called composite. So like 4 is divisible by 2 and 4. It's called composite. Okay, so we've got a list of numbers here from 1 to 50, and you'll see in your homework, your assignments, that use the, I don't even know how to say his name properly, but Eratosthenes or Eratosthenes, I don't know, something. Use his method to find prime numbers. And so what we're going to do is we're going to try to do this, and we're going to do this example here first, where we've got a list from 1 to 50, and he says that if you take and start breaking it down, these steps down below, if we follow that process, we can cross off all the numbers quickly that are not prime and be left over with the ones that are prime. Okay, so he says to cross off all the numbers, or he says specifically in this step, cross off 1. He says cross off 1 because it's not prime. Okay, and then he says to circle 2 because it is prime, and then to cross off all the multiples of 2 because they would not be prime. So we can go ahead and cross off all the even numbers here. And if you notice, you've got all your even numbers are in a column. So you cross off all these even numbers because they are not prime. So this is just a methodical way to do this. And you can continue and do it past, oops, 3's there. So it says the next number in the list that has not been crossed off is 3. So we just kind of work our way up. So we're saying, all right, well, 3, that's prime. So if we circle 3 and say it's prime, then we have to cross off all the multiples of 3 that are left over. And so we've got 9 here. It's divisible by 3. 15 is divisible by 3. And then as we continue down the list, we just continue to cross off all the ones that are actually divisible by 3 that we haven't crossed off already, of course. All right. I believe that we've got them all. So then we've got step 4, which says to circle 5. So notice how we've got 2's prime, 3's prime, 5's prime, and then we have to cross off all the leftover multiples of 5. Because if 5 goes into it, then obviously it is not prime. So 25's here left over, 35's here left over, and that was everything that's crossed off, or that is divisible by 5 that's left over. So here we've got to circle 7. Notice we've got 2, 3, 5, 7's left, and then it just has one multiple left that's not scribbled out, and that's 49. So we scribble it out. And then the next prime is 11, and it's greater than the square root of 50. And this is where it's interesting, because it says as soon as you did that, you can stop looking for composites and circle all the remaining numbers in the list. 13, 17, 19, 23, 29, 31, 37, 47, 41, 43 are all prime. So if we think about it, we'll see that it's impossible to have a composite number of the form of A times B, where both A and B are 11 or greater, yet the product is less than 50. So what we're saying is, as soon as we get to 11, it's greater than the square root of 50. So in other words, if you get to a number and you square root it, 49 square rooted is 7. And so the next prime number past 7 is 11. So basically the numbers between 7 and 11 If we're past that, if we go 1 past the square root of 50, 50 is just past this, just bigger than 7. So if we go and find the prime number past that, all the numbers that would be left over, if you've crossed off all the factors of everything that was below that number like we did here, they have to be prime. So it's just a very straightforward process to methodically get rid of all the composite numbers. If you get rid of all the factors of the prime numbers below the square root of whichever number you counted up to, you'll be left over with the prime numbers. Okay, so let's determine whether or not these numbers are prime or composite. So based on what we just talked about this guy's method, we can basically methodically think through about 83's square root. So if we get rid of or if we divide it by all the numbers that are divisible, or all the prime numbers up to the square root of 83, which should be just less than 8. So if we go 2, 3, 5, 7, if 83 is not divisible by any of them, then it will be prime. So I'm sorry, I misspoke. I said 8, I meant 9. I was thinking 64 instead of 81. 81's 9, of course. And so what you do here is you take 83 and you divide it by all the prime numbers less than 9. And so if we take an 83 and divide by 2, it doesn't work. Divide by 3, it doesn't work. Divide by 5, it doesn't go in evenly. 7. And so if you keep dividing it by those prime numbers, you'll find that nothing works until you get up to 9, and 9 doesn't work, and the square root of 83 is between 9 and 10 here, and so as soon as you get to 9, which is not prime, but because we did 7, and we got all the way up there and found that none of those work, the definition here is we're saying that if you get up to the square root and have divided by all the previous prime numbers up to this square root, which would be all the ones up less than 9, then 83 is prime, and it is. 83 is prime. There is not a number that goes in evenly. And so let's take a look at 87. 87, there we go. Oh, come on. Here we go. 87 has factors of 3. Now notice 83 is a little bit less than 87. 87 square root's a little bit bigger, and so you would do the same process. You would take 87 and divide it by the prime numbers, and so we have 87 divided by 3, whereas 83, we would have done the same process. You would have divided by 3, you would have divided by 5, 7, and it wouldn't have worked. I skipped 2, but you get the point, I hope. And so here, 87, when you start dividing just in the same straightforward way, we actually do get one that works. So 397, we do the same process. We've got to figure out what the square root is. So if you do the square root of 397, you get 19.92. And then so to determine if it's prime, we have to check all the primes less than or equal to 19 to see if they divide by 397. So our list up to 19 is going to be 2, 3, 5, 7, 13, 11, 13, and 17, and 19. So you have to divide 397 by all these numbers, and if any of them work, then it's not prime. If they all don't work, then it is prime. And here, when you do all the division, it is, in fact, prime. Okay, so again, what I'm saying is I'm not going to spend the time doing it here, but divide by all the prime numbers up to 19.92, and then if none of them work, then you can be confident that this number is prime. And so what we can do here is, rather than actually do the division, we can run things through divisibility tests. And so the text talks about questions of, is this number divisible by 3? Is this number divisible by 5 or 4? And you can actually just take your calculator and divide and see if you have a remainder. Would probably be the shortest and fastest way. But here are some divisibility tests that can be nice little tricks to know, have a sense of whether or not a number is divisible by 2 or 3. 2, and especially with 3. 2 is pretty obvious. I mean, if the number is an even digit at the end, then you know it's divisible by 2. And the 3 is nice. This is a nice rule that not everyone knows about. If you add the digits, and the digits, the sum of them is divisible by 3, then your actual quantity is divisible by 3. So, for example, 21,021, if you add the digits, the 2, the 1, the 0, the 2, the 1, that equals 6. Because the sum is divisible by 3, and you always get a smaller number by summing the digits. Because this is divisible by 3, then this big number is divisible by 3. It's a really cool trick, and it works for 6 also, but you've got to do, it's got to be divisible by both 2 and 3. So in other words, this number up here, this 21,000, would have also been divisible by 6, because 2 goes into the sum and 3 goes into the sum. But if it had been like 9, if you had gotten a 9, this is divisible by 3, but not 2, and so 6 wouldn't go in. All right, and then 4 has a nice little trick as well. The number formed by the last 2 digits is divisible by 4. So if you just look at the last 2 digits, and if that's divisible by 4, then 4 is going to go into whatever your number is. And of course, you can keep reading through those. It's a great little check to see if a number is divisible. So we're going to check this 11,552, which is kind of covered up on my thing at the top there to record with. But your job is to see, and very similar in your homework, to just check off whether or not each of these work. And so, obviously 2 is going to work because it's even. And if I sum the digits, we've got 1, 1, plus 3, so we've got 4, 5, plus 5 is 10, 12. So the sum of the digits is 12. So that means that 3 is going to work. If we take the last 2 digits, 52, and see if it's divisible by 4, then you know that 4 goes in or doesn't go in, and 52 divided by 4 gives you 13. It goes in evenly, so 4 goes in. 5 is not going to go in because we don't end in a 0 or a 5. 6 will go in because this sum of the digits is 12, and that is divisible by both 3 and 2. So then we check for 8. 8 says the number formed by the last 3 digits is divisible by 8. So we got to take 352 divided by 8 gives you 44, so 8 goes in. And then 9 says the sum of the digits is divisible by 9. And of course 12 is what the sum of the digits was, so 9 is not going to work. And then 10 also will not work because it is not ending in a 0. So kind of a cool quick check to, I would probably take a picture of this, or earlier when I didn't have a lot of writing on it. It's like a nice little chart to figure out whether or not something is a factor. So we got the fundamental theorem of arithmetic. It says that every number greater than 1 is a unique product of prime numbers, except for the order of the factors. So the product says the product could mean a single prime number. In other words, even a number like 13, you can say 1 times 13. So what we're going to do is we're going to learn how to factor using my hockey stick method. So this is 4,620, and we're going to break it down into its prime factors. And what I'm going to do is I'm going to break this up, since we're getting a little long here, into a second link. So click the next link to watch further.